Good morning, everyone, and good evening, depending where you are. So today you are assisting to the OPAL RT webinar about the power hardware in the loops, commonly called PHIL. So today we have the chance to have 5 members where we talk different subjects. So the first member will be Dr. Sudipta Chakrasborty. He's actually leading our US R&D activities for OPAL RT, and he's our Director of Energy and System at OPAL RT as well. Sudipta worked on his career on a lot of projects on grid integration of renewable energy, such as high power density IEC PV inverter development for modular power electronics, and as well as development for new hardware in the loops based on method of inverter testing. Today, Dr. Sudipta will talk about what is a PHIL and all the basic and what you need to know when you do your first PHIL application. Then after that, we have the chance to have 2 co-hosts of Sandia National Labs, Mr. Jay Johnson and Mr. Adam Summers. Both of them work at the technical staff at Sandia National Lab. Jay is the primary members, and Adam is a member of the technical staff as well. Both of them work on a lot of projects with renewable energy and research, involving like DER optimization, HIL, smart grids on the subject. So today they will talk about doing powered hardware in the loops to test PV inverters. Then after that, we have François Tempez, who works at OPAL RT. He's currently a technical sales rep in Germany, but before that, he worked a lot as an FEA for OPAL RT and performed a lot of integration of PHIL in Europe. So today, François Tempez will talk about some big European PHIL that OPAL RT did in the past, and what is the success that we have. Then we have myself, Mathieu Hainaut. Actually, we're a customer solution architect, so I help the sales rep to define their applications, especially in power hardware in the loops. So today I will talk to you about the new amplifier that OPAL RT developed, and as well as other accessories and how we can help you at OPAL RT for PHIL application. So we can start with our first member. So the first member will be Dr. Sudipta, who will talk about PHIL application. So I will pass the presenter to Sudipta.
Thank you everyone for joining this webinar. As Matthew mentioned, I will be talking about the basics of power hardware in the loop. So let's go to my slide. So first, before going into the power hardware in the loop, we need to understand what is real-time simulation. For a real-time simulation to be valid, the simulator used must accurately produce the outputs of the simulation within the same length of time that its physical counterpart or the real-world system would do. So in fact, the time required to compute the solution at a given time step must be shorter than the wall clock duration of the time step, as shown in this figure B. This permits the real-time simulation to perform all the operations necessary to make this relevant, including driving the IOs, which will be needed for the hardware in the loop, as we'll be seeing later slides. So hardware in the loop, what is that? Basically, hardware in the loop testing utilizes the real-time simulation to connect and test actual hardware devices with simulation of rest of the systems and test environments. This allows user to perform realistic closed-loop tests without the need of the testing on a real system. So as you can see in this figure, the real-time simulator is the one that is running the real-time simulation, and it is connected to the actual system, such as controllers. It can be different types of controllers, such as SCADA, EMS, GMS, microgrid controller. It can be power electronics controller, or even vehicle ECU. And you can also connect some of the devices, such as protection devices, smart sensors, along with this real-time simulator. Now, this kind of setup typically refers to the low voltage, low current signal level connection between the real-time simulator and the actual system. And the loop has been closed by the measurement from the actual system back to the real-time simulator. But for power hardware in the loop, as we will see later slides, can be employed for higher power testing using the same methodology. So in power hardware in the loop, involves in creating this virtual power interface between the digital simulations and the devices under test. So as shown in this figure, now we have a power amplifier between this real-time simulator and the devices under test. And the power amplifier is basically amplifying the low voltage or current signals from the real-time simulator to the actual voltage and current so that you can now connect the actual at power devices such as power converters, machines, drives, even microgrid switch, point of common coupling, batteries including BMS, electrical, drivetrain, vehicle charger, etc. So typically this power interface involves power amplifier, which must be selected carefully depending on the application. PHIL setup, as you can see, is much more complex and typically more costlier than this regular HIL setup, mainly due to the cost of the amplifier, as well as due to the sensing hardware needed to close that loop. So there are different types of test beds, as you can see, and was very well depicted in this paper I mentioned here by MIT Lincoln Lab. But basically, there are simulation, there are controller hardware in the loop, power hardware in the loop. You can have a power test bed, which is a replication of a smaller scale replication of the full system, or you actually have the actual fielded system. Now, each of them has some positives and negatives in terms of the cost, test fidelity, and the test coverage. For example, test fidelity depends on the purpose of the testing, how good is your model, and what is the test setup is. For a power test bed, fidelity depends on the equipment used and the similarities between that and the real installation. Whereas test coverage depends on the purpose of the testing and flexibility of running various what-if scenarios. So pure simulation doesn't allow testing of real devices, but if you have a very good model, then it is a powerful tool for design studies because you can run different scenarios in that way. On the other hand, full system testing is very good in terms of fidelity, but on the other hand, the coverage will be less because it's not as flexible to run multiple scenarios without creating problems in the actual system. For example, control hardware in the loop, on the other hand, provides the best coverage when you are testing a control system, such as microgrid controller, allowing the fault scenarios, transitions, dispatch scenarios, etc. What we found, power hardware in the loop can provide a good balance between the test fidelity and test coverage because you can actually build a system in PHIL which is closely replicate the full system by either the simulation part or by the actual power devices. And then you can run lots of different scenarios that is not, you'll be able to do it in a full system. So basically it can provide a very good test coverage, but it will be cost less than a full system testing or like a field device testing. Some benefits of PHIL, it allows developers to test a wider range of device characteristics than analog benches or dynos with less maintenance and setup time. By that way, it allows robustness of the hardware under test over a wider variation of parameters, test conditions, and faults. In addition to interfacing with the hardware, PHIL also provides testing and incorporation of the real-world communication network along with your power system testing. You can incorporate different types of protocols such as Modbus, DNP3, 61850, CAN, whatever you can think of. By that way, you can then incorporate the real-world delays, latencies, cyber events into the system-level validation. So PHIL creates a robust, flexible test and reliable test platform by allowing validation of a complex system-level dynamic interaction between multiple devices at power without costly field demonstration or detailed device models. It also enables tests that are not feasible or too risky to do in the real system, such as fault on the feeder, overspeed on the motors, because those kind of tests, if you do it, it either impact the customer or it can create some safety risk if you are doing it on the real system. So PHIL will provide a good balance between what you can see when you try to do those kind of testing. In a typical PHIL setup, you have an amplifier, you have the real-time simulator with inputs and outputs, shown in this figure. You also have the sensors to feed back to the simulator. But most important part, or sometimes people forget about some other parts, which is that you also need to have the real-time models along with some interface algorithms, some filtering, some compensation, protection, etc. So first we'll talk about the amplifier. So amplifier selection is very technical and is extremely sensitive to the application. For example, I'm giving some sample specification on the left-hand side of the screen. It starts always with what application you are going to use it for. Is it a motor application, grid application, inverter, microgrid, whatnot? Then the next question is the power rating. How many number of phases you want to do? What kind of capabilities you want to simulate? Do you want to just get the AC output of that amplifier? Do you want to do the DC? Or or do you want an amplifier that can go from DC all the way to AC, and in some cases to the high frequency AC? Another big question that asked always is like whether we need a 2-quadrant or a 4-quadrant amplifier. So I am giving this figure in the middle. Basically, 2-quadrant amplifier can only source power to the load or the devices under test, whereas the 4-quadrant amplifier can both source and sink power using that amplifier. Now, 2-quadrant amplifier used to be popular some time back, but they always requires additional, or they sometimes require, I would say, additional sinks in case of the application such as say PV inverter testing, where your inverter power has to go somewhere and your amplifier cannot sink the power. So you will then need a load, some form of a load between your amplifier and then the inverter. 4-quadrant amplifier are getting more and more popular nowadays because they give more flexibility. But then not all 4-quadrant amplifiers are created equal, because some can absorb 100% rated power back when you are operating it as a sync mode, but some cannot. So you have to be careful when you are specifying your amplifier. Then there are different types of amplifiers, such as linear or switching versus switching or non-linear type of amplifier. Basically, it depends on what kind of power electronics they have inside. And for a linear amplifier, for example, will have higher bandwidth, faster response, lower flex, but they will provide lower flexibility. They are bulky and costly. On the other hand, switch mode provide lesser bandwidth than the linear one, but it has lower response. It provides higher flexibility, and it can be easier to connect for the higher power. Then there are other specifications such as nominal voltage, current, peak current, nominal frequency, frequency range, frequency resolution, output impedance, harmonic distortion. Amplifier slew rate is another important thing. How fast your amplifier responds when you send a set point to that amplifier. How you connect to that amplifier, what is the feedback measurement, amplifier size and weight, price range. All these parameters you need to at least define initially before you decide on which amplifier you're going to buy. So I give some example of this amplifier manufacturer, and as Matthew mentioned, you will hear about a new one later part of this webinar. Other considerations for PHIL testing include interface algorithm. So there are different types of interface algorithm that you can utilize when you are interfacing between your simulator and then the hardware. And this particular paper mentioned here gives very good details about each of those algorithms and what is their pros and cons. I give an example of the most common one, which is the ideal transformer method here, ideal transformer model here. In this particular case, your voltage simulator or your simulator will give the voltage signal for your grid amplifier, and then the amplifier current output from that amplifier is measured back and fed back to this simulator model to close that loop. Not only the interface algorithm, filtering and compensation is also important. Noise due to sensors, EMI, EMC can create issues in interfacing. So introducing filter in hardware or software can create or can mitigate that problem. But on the other hand, they will create some unwanted delays, and you have to do some compensation algorithm to mitigate some of those filtering effects. Stability analysis has to be done because closed loop PHIL system, including simulation, amplifier, sensors, can become unstable for certain operating condition, and this can damage the equipment or result in loss of simulation fidelity. Just a sample of a PHIL stability analysis. In this particular case, it's a simple circuit where you are doing the analysis of the stability of the whole closed loop system, including the amplifier, including the feedback sensors and the loads. Basically, it just shows that you have to have something similar for each of your application, because you will find the stability will depend on the load power to the short circuit power, types of load, damping of the source impedance, power amplifier bandwidth, simulator sampling frequency, feedback filter bandwidth, etc. And there are different methods of stabilization of this kind of system can be found in references. One thing I also want to emphasize here that the determining the best interface and stabilizing methods to ensure system stability and maximum accuracy must be done on a case-by-case basis. Even if you see a paper and you think it will work, but you have to do this kind of analysis before you kind of jump into that type of system. Some PHIL example. The first one is for an inverter testing example. In a typical conventional anti-islanding testing of an inverter, you typically have a actual inverter, which is GR under test, an actual load bank, RLC load bank, and then you have an island switch. So basically the idea here, you open the switch and see if the inverter can detect that islanding and disconnect itself from the grid. Because if you have a tank RLC load bank, then if you don't have a proper islanding algorithm, then this inverter can keep working and can create some possible equipment damage. This is a common setup that has been used for last 10 years or more for anti-islanding testing of the inverter, single inverter. But the question becomes nowadays, when you have high penetration, say PV type of scenario, how multiple inverters will interact with each other and how they can sensitize or desensitize this islanding detection method. So to address that question, this particular test setup was done at NREL, where we have 3 actual inverters connected to the circuit model, like islanded circuit model. And that circuit model was done at OPAL-RT simulator, where you actually can then create different what-if scenarios with different grid impedances, different types of loads, and different other scenarios to see how this inverter, the smart inverters with different advanced function, will work together when they are actually put into the field. I have a second example, which is more system level. In this particular case, this is a ADMS testbed, which is Advanced Distribution Management System testbed. In this particular case, they are actually, it is also done by NREL. They're actually connecting the model of the large-scale distribution systems for testing different ADMS algorithm. And not only that, they're connecting different control devices for controller hardware in the loop, and then connecting different power devices like inverter for the power hardware in the loop. To create a multi-scale, multi-platform test setup, which involves actual power and the control hardware. The last example I have is a microgrid testbed, which is a cyber physical testbed, including a grid model, which is a real-time model of the electrical system in the OPAL-RT platform. Also, we have a real-time network simulator model in a platform called Omnet++. And then the physical hardware in this particular case included a simplified microgrid controller, power meters, a smart PV inverter, and a battery storage inverter interconnected using this PHIL techniques. So this particular work has been done to see how this communication latencies, delays, and communication event can impact not only the operation of the microgrid, which you can see here, but then when this type of microgrids are connected to the grid, how this kind of network latencies will impact not only just the microgrid operation, but the operation of the whole power grid. And you can find more details in these papers I mentioned in my slides. With that, I will end my presentation. Thank you again for joining this webinar. And I believe now you'll see some poll questions, and after that, you will hear from the next presenter.